So still anyone there to join? Okay. Okay. We'll start the session. In the last session, we have discussed the introduction to the RISC-V processor, right? So what is mean by RISC processor and where we will use the RISC-V and what are the different types of technology like RISC-V and CISC where these technologies are used, okay? And the architecture of RISC and we explained the five-stage pipeline architecture also, right? So what are the different stages or involving in the RISC-V pipeline architecture and all. Okay. So, okay, let me ask few questions. Um, so can you explain what are the different pipeline stages involved in the RISC? What are the different pipeline stages involved in the RISC? Five stages. Okay, what are the stages?
Fetch and then decode access memory access and then register write and then execute.
Okay. What is mean by ISA in RISC processor?
Means like instruction set architecture it is actually.
Okay. Okay. So how can we convert the machine assembly level language into the machine level language? Like how can we convert the assembly level language into the processor understanding language? Or otherwise, how can we convert the high level language into the machine level language?
And by using compiler
Mhm. Okay. Okay. So, okay, let me recollect all the things like just we'll briefly discuss what is mean by RISC-V and what are the different type of pipeline stages out there, what is the block diagram and all, so that we'll get the idea. So whoever not attended for the previous session, so they will get some idea, right? So, yeah. So, how many pipeline stages are involved in the RISC-V processor, first of all? So, there are five stages, right? First is the fetch stage and decode and the register, execution, memory, and the write back. So, first, how will fetch the data? Like here, if you see there is a block like instructions memory. That means the instructions will load into the instruction memory in a sequential manner. Sometimes it may be in an unsequential manner. Then the processor will read these instructions, whatever different type of instructions we are giving, like there are different types like immediate type or register type or branch type. Okay, whatever the different type of instructions we are giving, the processor will read the instructions and the processor have the special purpose register here called the program counter. Okay, it is a special purpose register. We have different types of registers, right? General purpose registers, special purpose registers. So here program counter is a special purpose register which is used for the processor. And there is a here the programming will be always suppose here the program counter will be incremented plus 4 always. Okay, so we'll take from 0 4 8 12 16 like that, because here we are using everything in a byte addressing, right? So that's why program counter will use will increment plus 4 every time. Okay, so PC is equal to PC plus 4. like that. So that is how the processor is fetching the instructions from the memory, and the decoder will decode the instructions based on its type. Okay, based on it immediate type or register type or load and store type. Based upon that, the decoder will decode the number of instructions. Okay, next one is the execution stage. Whatever the data is getting from the decoder, that will be sent to the arithmetic and logical unit. Okay, ALU, right? So ALU means it performs the both arithmetic and logical operations. Okay, which is nothing but execution stage. Okay, so whatever the results are, okay, based upon the different type of operations, we have addition, subtraction. In logical operation, there will be AND or XOR, like that, right? So whatever the results are there, it will be stored in the memory or into the registers. Okay, we'll have some parallel registers here, which are getting here. So it will store the data into the registers. Okay, next one is the memory stage. What is the memory stage? That means it will write all the values into the memory, like write or read operation. Okay, it will perform the write and read operation. So it will write all the values into the memory, or it will read all the data from the memory. That is a memory state. And next one is a write back stage. What is a write back stage? Is nothing but the result, whatever the results are there, it will be write into the some register file. Okay, after execution stage, the result will be getting right. So those results will be written into the register file state. Okay, so these are the different five stage pipeline stages we have in the RISC-V processor. Okay, so mainly why we are using here instruction set architecture. Okay, based upon the instruction set architecture, we are doing all instructions and all, right? So why? Because mainly the CPU depends upon the CPU performance will depend upon the compiler. Okay, and whatever the preferable programming language based, we are using high level language, right? A high level language in the sense C or C++ or Verilog. Okay, based upon the preferable programming language, and whatever the algorithm we are using, different kind of algorithms, and mainly ISA. Based upon the ISA also, the CPU performance will be dependent. Okay, based upon how instructions we are using. A RISC means it is a very reduced instruction set, right? So based upon the reduced instruction set, the CPU performance will be dependent compared to the complex instruction set. So the reduced instruction set have some advantages, right? So because of CPU performance, ISA is very used. Okay, so can you tell me why multi-stage pipelining is necessary in the RISC-V? What is the importance of multi-stage pipelining? To speed up the process. Okay, so we can do all the parallelly, right? Fetching, decoding, execution. While one instruction is in decoding stage, we can fetch another instruction. Like that, multi-stage pipelining means it process the speed, high speed. Okay, and more number of the instructions will be executed parallelly. Okay, so that is mainly why the pipeline execution. And now we'll discuss how we'll translating the high level language into the binary. Okay, high level language, like mainly the how the RISC-V work means the processor should understand the binary language, right? So based upon that, we are converting the C code or Verilog programming or C++ into the binary format. So how it will be converted? See here, suppose this is the high level language in the sense Verilog or whatever C++ we are writing here. And after writing the high level language, giving to the compiler. Okay, what is the main use of compiler means it will convert the high level language into the assembly language. Okay, what is the assembly language? Assembly language is nothing but the instructions. Okay, for ARM or x86 processors, RISC-V processors, we have different types of instruction set, right? So it will convert into the instruction set. Okay, can you tell me what are the difference between high level language and assembly language? What are the differences between high level language and assembly language?
Assembly language is more related to hardware. It is not portable from one processor to, one type of processor to another type of processor. But high level language is portable to any platform.
Okay. Okay. Any other answers? Okay. High level languages are nothing but, as we discussed already, these are C or C++ or Java, System Verilog. These all are under high level languages. Okay. Whereas assembly language is nothing but present we are using a RISC-V processor instruction sets, ARM instruction set, and there is a x86 processor from Intel company. Okay, there they use some of the instructions, some of the complex instruction set. Okay, so mainly in high level language, there will be a complex data structures like we'll use the arrays, class based verification, or OOPS concepts, all these things. But in assembly language, we only use word or integers, bit, byte. Okay, so everything. Suppose if you want to do the addition operation of between two source and one destination, so what will be the size of two source and one destination? Maybe it will be in word size. Word means 32-bit size. Okay, half word, or it's a byte or a bit. Okay, or it is an integer type like that. Okay, so here here we'll perform both arithmetic and logical operations. Okay, here like sum equal to x plus y like that. In assembly language also will perform both arithmetic and logical operations. Okay, as we seen here, like immediate type or register type or branch type or jump type. Okay, every type we have the arithmetic and logical operations. Okay, and high level language mainly it is how we will verify. Suppose if we design any hardware by using the high level language, okay, mainly we will use for verification purpose, we'll approach some softwares like UVM test benches, okay, or Verilog HDL, system Verilog. These type of languages are used for software verification. But whereas for RISC-V, it is an assembly program which is a hardware. Okay, so another thing is here we will use the control transfer instructions like a branch type or jump type like that. But here we'll use if else conditions, if else or for loop. Okay, these type of conditional statements will be used. Okay, so after converting the assembly language by using the compiler, this assembly language must be converted into the binary, which is understandable by the processor. Okay, internal processor. So the processor language, hexadecimal language, like the assembly level language, will be converted into binary language by using the linker. Okay, so these are the main basic things of difference between assembly language and high level language. So everyone got the idea, right? Everyone got the idea, right?
Yes, ma'am.
So what
Yes, ma'am.
is mean by this binary language? How these, suppose here we are writing some instructions and I'm telling the instructions are converted into the binary language. So how these instructions are converting into the binary language? Okay, how the internal system is going to understand the instructions. Suppose there is a simple instruction. I'm telling, suppose there is a addition. Okay, addition of register type or immediate type, whatever. So it is performing the addition between two source registers. Between x86 is a one register and x8 is another register, and it and 3 is a destination register. Suppose um Okay. Suppose here not sorry, here 3 is opcode. Okay. So here X16 is a source register and destination register X8 and 3 is a opcode. Opcode in the sense in the different types there are different type of instructions, right? So I type means one opcode, it have one opcode. Or means it have one opcode. That means internal system will understand. Okay, suppose 0 1 0 sorry 1001 means it's a OR type, or 1100 means it's I type. Like that, it will understand internally. Okay, so here 3 means 0 um 011 means addition operation, or 010 means subtraction operation. Okay, like that we are passing the values here. Okay, so here addition means here we'll have the 3-bit which indicates the 12-bit. Okay, this add will be converted into the 12-bit data in a binary format. And x16 is nothing but what are the values of x16? 10000, and x8 is nothing but 1000, and here the opcode value is nothing but 011. So here we'll get the 12 bits of addition operation. So this instruction will be converted into the binary format like this. Okay, this instruction is going to convert into the binary format by using the linker. For that purpose, here in RISC-V, we are using RV32I instruction set ISA. Okay, based upon that, all different types of instructions are going to be classified in a different ways. Okay, so what are the different type of instructions are there? How we are converting the instructions into the binary language? This is the main thing we are going to learn today and tomorrow. Today I will cover all the basic things, and tomorrow Banu Teja will cover all like how we'll write the different examples. Okay, he will cover different examples for all instructions. Today I will tell how the brief explanation of all type of types. Okay, instruction types. So everyone understood why we are mainly using ISA, why we are using instruction set, different types of instructions, what is the need of instruction, why we are converting, why we are using those frame formats, because every instruction has some frame format. Okay, based upon the format only it will convert into the binary, because the processor need to understand in that way. Okay, so for that purpose ISA has it is a golden reference. Okay, by using it have all the predefined things. Okay, by using these ISA as a reference, we are going to develop all different type of examples. Okay, did you understood? Everyone got clarity here? Everyone got clarity here?
Ma'am,
Yes.
ma'am, that means like based on the frame format, we'll be communicating with the RISC-V.
Yes.
Okay. Okay.
So here
Uh,
frame format in the sense, suppose if you take any immediate type, in immediate type we'll have like one source, one immediate value, and one destination. Based upon opcode and based upon the instructions, we'll convert that values into the binary value. So that what the binary value is going to understand by the system, by the
that
processor,
means,
internet.
yes, ma'am. There are different kinds of like frame format, that is RI, and then these RI are defined by ISA.
Yes, yes.
Okay.
Okay, what is mean by ISA? ISA is nothing but it is like interfacing between the low level software and the hardware. Okay, so what is mean by software? Software is nothing but the compiler, assemblers. These are the software. Hardware in the sense processors. Okay, so this is the interfacing between the software and the hardware. Okay, so that's how by using these instructions and all we are going to convert. Okay, like it is like a golden reference which can be used basically by the compilers. Okay, so it support all the instructions based on the specification. Every processor have some specifications, right? Based upon the like market requirement, will get every yeah, will get updates in the specification. So based upon that, the compiler need to be work. Okay, so we'll design the compiler according to that. Okay, so by using the ISA as a golden reference, we will implement the RTL design at all. So that is main importance of ISA. Okay. Did you all understood the importance of ISA here? So here in this we are using RV32I instruction set. RV32I instruction set. Okay. Clear? Any doubts? Okay. See, if you see RV32 instruction format, we have different types of instructions. Okay. So like we have OR type. First one is the OR type. OR is nothing but register to register. We are transmitting the data from register to register instruction. Next, I type. I type in the sense register immediate. Okay. Will send the data, immediate data. And S type means a store. In S, we have both load and store type. And B means branch type. Different type of instructions are there in branch type. And U in the sense load or upper, like a load or add upper immediate. Okay. So U means load or add upper immediate. And J means jump and link. J means jump and link. So now today we'll see all the instructions briefly. So how each instruction is working and all. So yeah, these are the different type of instructions. First one is a OR type. First we'll see the OR type instruction. See, total in RISC-V 32-1 instruction, we have these many different type of instructions. Okay, so each element have the 32 bits. If you observe here, each element have 32 bits. Okay, in that 32 bits, the opcode will be defined for first 0 to 6 bit, then destination, then source, then functionality. Some format have the two number of sources, like a register type. If you see, there are two number of sources, RS2 and RS1. But whereas I type have only RS1 as a source register and immediate value. Okay, we'll send the immediate value. Like that, S type also have the two source registers and immediate value, like a B type. So it depends upon different instruction formats. Okay, so each element have the 32-bit, and RISC-V instruction format have both instruction and the data and address. So it is mainly byte addressing. As we discussed, it is mainly byte addressing, like 0, 4 incremented with a 4, 4. Okay, and the address bus of RISC-V processor is a 32-bit. As we know that here we are using RISC-V 32-bit address. So maximum address, how much, what is the maximum address we can store if 32-bit address means? How many locations will be there? How many number of locations will be there for 32-bit address? The size is 32-bit. How many number of locations will be there? Thirty-two is nothing but 2 power 32 number of locations will be there, right? We can do the next type. First one is a OR type. Okay, so if you see, these are the different type of instructions are there. Suppose OR type. Okay, or in OR type we have addition, subtraction, XOR, OR, and shift logical, left logical, shift right logical, shift right arithmetic, and set less than, unsigned. U means unsigned. Okay, so this is the FMT and opcode. If you observe the opcode here, what is the value of OR? For OR type, opcode is 0110011. Okay, so based upon the addition or subtraction or XOR or AND, we have the function. Okay, see here, if you observe 0000001001101. So based on the function. Okay, so next one is a function 7. Function 7 is a 7-bit and function 3 is a 3-bit. Based upon that, we'll have two sources, right? Two sources and one destination. Suppose if you see here, for OR type, so what is the value of OR? It is a destination. Okay, so function 3 means based upon it is suppose if you want to do some addition, or here if you want to do some subtraction operation means what is the value of function 3 is a 000. What is the value of function 7 is a 0100000. So here we'll get 000, and for function 3 will get function 7 will get 0100000, and whatever the value source 1, if you want to transmit like a 3-bit or 3 or 4, so based upon that the byte will convert into the binary, the destination. So what is the value of opcode? For every type of instruction there is a opcode, as we told here, right? So here opcode is a 0110011. Like that, for immediate type, opcode value is a 0010011. So that internal system can understand easily based upon the opcode, okay, which type of instruction it is. Okay, so if you see here addition, in immediate also we have add I in the sense it will denote like immediate. Okay, add I, XOR I, or I, and I, SLLI, that means shift left, shift logical left immediate. Okay, shift right logical right immediate. Next, shift right arithmetic immediate. Shift left shift left immediate. Shift less than immediate. Okay, shift LT means a shift less than immediate. Okay, so yeah, these are different. So if you see the function 7 here, for function 7 here, for immediate value we are taking these type of values. And for register, suppose register type means we have register address and the register source 1 and register source 2. But whereas in immediate, we have only one source value, one source, and next one is the immediate value. Okay, so what is that immediate value? In the sense xt immediate of 11 down to 0. Can you tell me what is that sxt? Sxt is nothing but sign extension of immediate value. Okay, we have sign extension, right? Unsigned or signed, like that. So based upon that, we'll check this thing. Okay, so these are different type of instructions. Like we have load byte, load half, like load and store instructions. Like S type. S type means store byte, store half, store word. Okay, opcode. If you see opcode, that is a different opcode. Here we have M of RS, one source. Okay, so everything we'll discuss one by one clearly. Like a branch type. What is the opcode? What is the function 3? Like that. And jump, J type, I type, U type. So these are the different types of instructions we have. Okay. Everyone clear up to here? If you have asked what is the difference between function 7 and function 3, right? See, function 7 is nothing but whatever we have here, both arithmetic and logical operations, right? So for arithmetic operation here, 000, all zeros here. Okay, in two ways it defined. One is all zeros, one is 010 and 0000. Okay, these two are under a different category and remaining all under one category. Okay, so for that, for function 7, again we have sub functions. Okay, like in function 7, if you take, we have both arithmetic and logical, right? In arithmetic, we have sub function like addition, subtraction, XOR, like that. Okay, XOR is a logical, right? So to define the sub functions, we are using the function 3. These are the unique values. Okay. So yeah, did you understood now?